Let's see how we'll represent the syntactic structure of a sentence in a programming language. Since we've described the hierarchical structure of the syntax of an English sentence using a tree-like structure already, we can just use the tree data abstraction to represent this value. So this whole utterance, is that a big bug or a little bug, is a tree with root label SQ, which is a tag or syntactic category describing a sentence which is a question. It has two constituents, which are its children, a verb phrase, and a piece of punctuation. This dot here is actually a tag describing forms of punctuation, such as periods, question marks, and exclamation points. And that's just the convention that we use in order to describe this category. So the tree has two branches, and this first branch with root label VP will have 3 branches, and its first branch will have only one branch itself. But notice that this is not a leaf. Instead, this is a tree with one branch, whose branch is a leaf containing the word is. So when we write a tree processing function in order to work with a tree like this, it will encounter trees that have branches and a syntactic category or tag as the root label, and also will encounter leaves which have words in them. And sometimes what people say isn't a full sentence, it's just a fragment. Is that a little bug or a big bug could be answered with a little bug, which is not a well-formed sentence, which is why we gave it this syntactic category or tag of fragment. So let's represent this one in Python and see what we can do with it. Here's the tree data abstraction that we already developed. And here is how I would represent that particular fragment, a little bug, using a tree that has labels that are tags, as well as leaves that are words. I made one change that's different from the slide, which is that I included above the frag a root label. And this is just a convention from the data set that we'll use. All utterances start at root and proceed from there to have a particular kind of utterance, whether it's a fragment or a question or a whole sentence. So for this example, which is represented as a bunch of nested lists, I can treat it as a tree and call leaves on that example and get a little bug period. Now this is not quite how you write English. Instead, you write a little bug period, where there are spaces between and little, but there's no space between bug and period. So we're going to write a function that imposes those rules. Within the built-in string module, there's a list of punctuation. And when a question mark or a period shows up in a sentence, there's no space right before it. However, for $signs, there is a space before it. And so we're going to write that logic into a function. Also, when there are contractions like nt and is and we'll put those together into a list of words. They coming over. We want it to be the case that putting this together into one string doesn't put a space between they and but instead leaves those together, but make sure that there are spaces between coming and over. It got mad because I put an apostrophe in the middle of a single quoted string. Okay, so how are we going to achieve this? Well, here's the plan. We'll take a whole tree like this example. We'll get the leaves of that tree, which are words. We'll build up a string. And for every word that we add in, we have to figure out whether to put a space before it or not. There's no space if W is punctuation, except for $signs or a special case. And there's no space if W is in the set of contractions that I noticed in the data set. There might be more contractions, but those are the ones that I found. So if we're at the very beginning of the sentence, or we're not supposed to put a space, then we just put the word into the sentence. Otherwise, we put a space in and then the word. And now we have a function, words, which takes in a tree like this, and doesn't just gives us the list of the words in the tree, but actually writes it out as a sentence. Now we can manipulate the tree and then write out its words. So let's write a function replace, which takes in a tree such as example, takes in a tag such as JJ, which stands for adjective, and says a word that we'd like to use in place of all adjectives that happen to be in the sentence described by this tree. Since this example had only one adjective, little, we're going to replace that adjective with huge by calling replace in the example all adjectives with huge. How do we do it? Well, if the label at the top of T is equal to the label that we're trying to replace, then we need to return a new tree. It should have that same label at the top. It's still an adjective, except it's not little anymore. It's huge. So we have to add a single branch, which is a tree, with the word that we're interested in. Otherwise, we build the whole sentence by returning a tree with the same label that T had, but its branches will have all of the adjectives replaced with huge. Replace in each branch S with W for all the branches in the branches of T. So our example looks like this. The replaced version of our example, where the adjective is now huge, is itself a tree, still rooted at root, still a fragment, still a noun phrase, which has a, and still has an adjective just like before, except now it's huge, and it's a huge bug. At which point, we can call this an updated example and get the words of that in order to see what it would look like if somebody wrote it out.